We've got a big update, a huge update on our favorite interstellar object. It could be the biggest update in the solar system. Take a look at this. The 3I Atlas was getting way brighter, way bluer as it got close to the sun.
They're calling it the craziest astronomical event of the decade, and we're about to miss every single bit of it.
Now it is hidden behind the sun, and even during its closest approach, Earth-based telescopes are not going to be able to see it. What's worse, the images that NASA captured right before all this, well, we haven't seen those because of possibly the government shutdown.
In exactly 17 days, 3I Atlas will disappear behind the sun for 6 weeks straight. But what's got the world's top scientists losing sleep is that during those invisible weeks, this thing could execute a maneuver that traps it in our solar system forever, and we'll have zero ability to watch it happen. What critical events will unfold during that excruciating solar blackout? And who will be proven right or wrong afterward? Vanishing behind the sun. Here's why this particular blackout is so terrifying. 3I Atlas entered solar conjunction on October 21st, positioning itself directly behind the sun from Earth's perspective. 8 days later, on October 29th, it reached perihelion, which is its closest approach to the sun at roughly 130 million miles, about Mars's orbital distance. Now, you'd think perihelion would be the moment we'd want every telescope trained on this thing, right? It's the climax of the comet's journey, when solar heating hits maximum intensity, when the most dramatic activity should explode across its surface, except we can't see any of it. The sun's glare creates a blind spot spanning about 10 degrees in every direction, and 3I Atlas slipped into that dead zone at precisely the worst moment imaginable. We tracked this visitor for 3 solid months after its July discovery, watching it approach, measuring every detail we could capture. Then, right when things should get interesting, the curtain falls. But you see, this isn't just any comet. This is an interstellar visitor, something that's been wandering the galaxy for potentially billions of years before stumbling into our neighborhood. Its trajectory brought it remarkably close to Mars in early October. After perihelion, it'll pass near Venus and Jupiter. And that closest solar approach? It happens precisely when Earth is on the opposite side of the sun, when observation is impossible. So what might happen right now in this moment while 3I Atlas hides behind our star? Let us walk you through different possible scenarios that have scientists really terrified. The plasma cavity collapse. The first nightmare involves something most people have never heard of: the comet's plasma cavity. Once you understand what this is and what happens when it fails, you'll understand why astronomers are losing sleep. 3I Atlas isn't traveling through empty space. The sun constantly hurls out a supersonic stream of charged particles called the solar wind, carrying the sun's twisted magnetic field along with it. When that wind slams into a comet, something beautiful and violent happens simultaneously. The comet releases gas and dust that get ionized by solar radiation, creating a glowing plasma cloud called the coma. This plasma pushes back against the solar wind like an invisible shield, carving out what scientists call a diamagnetic cavity, essentially a protective bubble where the comet's own plasma dominates. The Rosetta mission to Comet 67P Churyumov-Gerasimenko let us watch this process up close for the first time in history. As 67P approached the sun, researchers observed the cavity growing, forming a bow shock where the screaming solar wind suddenly slowed from supersonic to subsonic speeds. The boundary of this cavity, the ionopause, acted like a force field. The interplanetary magnetic field couldn't penetrate it. But these boundaries just aren't stable, and under extreme pressure they can collapse entirely. Now think about what 3I Atlas will experience. Every hour it spends near perihelion, the solar wind intensity climbs. The pressure bearing down on that protective plasma bubble increases relentlessly. Rosetta showed us that even under normal conditions, these cavity boundaries can suddenly compress, expand, even temporarily vanish before reforming. But 3, I-Atlas isn't experiencing normal conditions. It's experiencing peak solar assault during the most active phase of its entire journey through our solar system. What happens if the cavity collapses? The comet gets hit with the full, unfiltered force of the solar wind. The magnetic field that was previously excluded suddenly penetrates all the way to the nucleus. The entire electromagnetic environment surrounding the comet could be violently reorganized in ways we've never directly witnessed with an interstellar object. The tail structure, the coma brightness, the ion emissions, everything could be fundamentally restructured. And here's what makes this really disturbing. When we finally see 3I Atlas again in November, we won't know what state its plasma environment is in. Did the cavity hold? Did it collapse and struggle to reform? Is the comet now surrounded by a completely alien magnetic configuration? Any conclusions drawn about the comet's composition, its activity patterns, its evolutionary state, all of it could be fundamentally wrong because we're missing the most important part of the story. But as terrifying as a plasma cavity collapse sounds, it might actually be the least of our problems. Because while the comet's electromagnetic shield might be collapsing, something far more violent could be brewing deep inside the nucleus itself. Explosive, volatile activation. Here's something most people don't realize about comets. They're not uniform chunks of ice. They're more like frozen time bombs with different layers of volatile materials, each with its own trigger temperature, each waiting for the right moment to explode. Water ice starts sublimating significantly around 4 astronomical units from the Sun. That's relatively tame, but beneath those water layers is where you find carbon dioxide, carbon monoxide, molecular nitrogen, exotic ices that remain frozen solid at greater distances. And they're all just waiting. So here's what makes 3I Atlas particularly unnerving. James Webb Space Telescope observations revealed this comet has an unusually high carbon dioxide to water ratio, approximately 8:1. That's among the highest ever recorded. This thing is absolutely loaded with volatile material that's far more reactive than regular water ice. As the comet plunges toward perihelion, solar heating doesn't just warm the surface, it penetrates deeper. Temperature gradients drive inward like invisible fingers, probing through layers that have been frozen solid for billions of years. Eventually, inevitably, that heat reaches ice that's never been warm before in its entire existence. When deep volatiles suddenly hit their sublimation temperature, the results can be catastrophic. Gas pressure builds under the surface crust, searching for any weakness. A crack, a fissure, a thin spot in the mantle. When it finds one, the results are explosive. Research on 67P showed that carbon dioxide outbursts are particularly violent. Dry ice sublimes much more aggressively than water ice, creating intense localized jets that can eject tons of material in minutes. More critically, these jets create thrust, real measurable thrust that can actually alter the comet's trajectory. Now imagine this happening to 3Y Atlas while it's hidden behind the Sun. The sudden brightness spike, the explosive expansion of the coma, the emergence of powerful new jets, all of it happening without any human eyes watching. We'll miss the entire event, but the consequences will be waiting for us. When 3I Atlas reappears in November, astronomers might discover its orbit has shifted, possibly by thousands or even tens of thousands of kilometers from pre-perihelion predictions. Even more disturbing, the outburst might fundamentally restructure the comet itself. If a large section of surface crust gets blown away, exposing pristine ice underneath, post-perihelion activity could skyrocket beyond all predictions. Or if the outburst ejects a massive dust cloud that settles back onto the nucleus, it could create an insulating blanket that chokes off all future activity. The comet that emerges might behave in ways that completely contradict everything our models predicted. And there's one more chilling possibility. The rotation rate could change. Asymmetric jets exert torque. If they fire hard enough, long enough, in the right directions, they can alter the nucleus's spin or even flip its rotation axis. 3. I-Atlas might emerge from perihelion tumbling in a completely different pattern than when it went in. The outburst scenario means we're missing the single most critical moment in this comet's entire passage through our solar system. But at least with outbursts, we're talking about changes to the nucleus itself, things we can eventually study and analyze. What happens when the changes occur outside the comet, in the structure that's supposed to tell us how it interacts with its environment? What happens when the comet's most visible feature gets violently severed and blown away? Tail disconnection events. Now, comet tails aren't permanent fixtures. They're not attached to the nucleus like hair on a head. They're dynamic, flowing structures controlled by forces most people never see. And those forces can be absolutely brutal. The ion tail, that beautiful glowing streamer that points away from the sun, is shaped entirely by the interplanetary magnetic field embedded in the solar wind. The ionized particles follow magnetic field lines like beads on invisible strings. Under normal conditions, it's elegant, but under disturbed conditions, it becomes a war zone, and we've watched the carnage happen before. In April 2007, NASA's Stereo A spacecraft captured one of the most violent events ever witnessed in cometary science. Comet 2P Encke passed through a coronal mass ejection. A massive eruption of plasma and twisted magnetic field launched from the sun. The wave of solar materials slammed into Encke's magnetosphere and literally severed its tail. In an instant, the entire ion tail was disconnected from the nucleus and blown away into space. Within minutes, a new tail began forming from scratch, but the old one? Gone forever. More recently, in April 2024, Comet 12P Pons Brooks, the so-called Devil Comet, suffered the same fate when a coronal mass ejection blasted it just days before its perihelion. The plasma wave ripped away its tail, leaving the comet to rebuild its entire ion structure. Now, think about 3I Atlas's situation right now. The sun has been increasingly violent during this solar cycle. Coronal mass ejections have become more frequent, more powerful. In September 2025, just days before 3I Atlas entered solar conjunction, the Sun unleashed a powerful CME that scientists calculated would collide with the comet's path. But here's the interesting part. We have absolutely no way to know if disconnection events are happening right now. CMEs could be striking 3Y Atlas repeatedly, severing and reforming its tail again and again, and we would be completely blind to it. Why does this matter so much? Because a comet's tail is one of our primary diagnostic tools. The shape, the length, the composition, the structure. All of it tells us about outgassing rates, solar wind interaction strength, and magnetic field orientation. If 3I Atlas experiences major disconnection events during its hidden perihelion passage, then the tail we observe in November will be newly formed, days or weeks old at most. Scientists will look at post-conjunction observations and try to model the comet's interaction with the solar wind based on what they see. But if that tail is brand new, formed after a catastrophic disconnection, then every single one of their models will be built on incomplete data. They'll be trying to understand the comet's behavior from perihelion through November, but they're actually only seeing what happened in the final days. Even worse, if the disconnection occurred precisely at perihelion, when we'd expect the most intense activity, then we've lost our best opportunity to study how this interstellar visitor responds to maximum solar heating. The preconjunction tail structure? Gone. The perihelion tail structure? Also gone, if it ever properly formed. We're left with whatever tail happens to exist in November, which might bear zero resemblance to what the comet's plasma interaction actually looked like during its most critical phase. But at least tail disconnections are dramatic, visible events that we can eventually detect and study after the fact. What about changes that are subtle? Changes that slowly dim the comet, making it fade into darkness just when it should be at its absolute brightest. What if, right now, 3I Atlas is quietly suffocating under a layer of its own dust? The dimming mystery. Everyone expects comets to brighten as they approach the sun. It's practically gospel in astronomy. More solar heating equals more sublimation equals bigger coma equals brighter comet. Simple physics, right? Except comets don't always follow the rules. And history is littered with examples of comets that mysteriously faded just when they should have been dazzling us. The mechanism behind this nightmare is called mantling or dust crusting, and it's more insidious than it sounds. Here's what happens. As a comet approaches the sun, sublimating ice carries dust particles into the coma. But not all that dust escapes. The heavier particles, the larger chunks, fall back. They settle onto the nucleus like toxic snow, building up over time. The Rosetta mission at 67P Churyumov-Gerasimenko showed us just how effective these dust mantles can be. Even a layer just a few millimeters thick can dramatically suppress sublimation. If the dust is fine-grained and compacted, it essentially seals the surface, choking off the gas production that makes comets active and bright. But there's another process that's equally terrifying: volatile depletion. Remember how we talked about 3I Atlas being unusually rich in carbon dioxide? Well, carbon dioxide ice sublimates much more readily than water ice. It starts outgassing at far greater distances from the sun. As 3I Atlas has been approaching perihelion over the past several months, it's entirely possible that much of its easily accessible carbon dioxide has already been depleted from the surface layers. Studies of 67P showed this exact phenomenon. The comet's southern hemisphere, which received intense illumination during perihelion, showed dramatically reduced carbon dioxide emissions afterward. The volatile-rich surface was simply gone, leaving behind water ice and a dust-laden crust. The comet transitioned from hyperactive to sluggish in a matter of weeks. Now imagine this playing out with 3I Atlas during its hidden perihelion passage. The intense solar heating could be rapidly stripping away surface volatiles. The dust being released could be settling back faster than it's being blown away. An insulating crust could be forming over the active areas right now, this very moment. When 3I Atlas emerges from solar conjunction in November, astronomers might be genuinely shocked to find it significantly dimmer than every prediction suggested. The coma might be smaller, the tail might be shorter. Spectroscopic observations might show dramatically reduced gas emissions, and scientists will scramble for explanations. Were our models wrong? Did we overestimate the volatile content? Is this normal for interstellar comets? And it gets worse. The dimming might not even be uniform. Maybe only one hemisphere developed a thick dust mantle while the other side remained active. When we observe 3I Atlas in November, we'll only see whatever hemisphere happens to be facing Earth at that moment. If we're looking at the mantled side, we'll think the entire comet has gone dormant. We might even conclude it's dying. But the other hemisphere could be erupting with activity, and we'd have no idea. The mantling scenario means 3I Atlas could undergo a fundamental transformation during the exact period we cannot observe it. But all of these scenarios, plasma collapse, explosive outbursts, tail disconnections, surface mantling, they all assume one thing: that we know where the comet actually is, and that assumption might be about to shatter in the most disturbing way possible. A drift in trajectory. Here's a question that should be simple to answer. Where exactly is 3I Atlas right now? You'd think this would be straightforward. We tracked this comet for 3 months. We calculated its orbit from hundreds of observations. The trajectory is determined by gravity, the sun's mass, and the comet's velocity. So how could there possibly be any uncertainty? The problem is that comets don't follow purely gravitational orbits. Those jets erupting from the surface produce thrust, real measurable thrust. Even gentle, steady outgassing creates what astronomers call non-gravitational forces. These forces are tiny compared to the sun's gravity, but they're constant. And over days and weeks and even months they accumulate. They push the comet off its predicted path by thousands, sometimes tens of thousands of kilometers. 1I Oumuamua, the first confirmed interstellar visitor, showed measurable non-gravitational acceleration, despite having no visible coma or outgassing. This mysterious acceleration sparked massive debate. Some scientists proposed exotic explanations like hydrogen ice sublimation. Others, famously Avi Loeb, suggested something far more provocative: artificial propulsion. Now consider 3I Atlas's situation. From October 1st through at least November 9th, Earth-based telescopes cannot observe it. That's more than 5 weeks of blind time during the period when the comet should be most active, when non-gravitational forces should be strongest. Every single day, every hour the comet outgasses, it experiences tiny accelerations pushing it slightly off the purely gravitational path. These accelerations depend on variables we cannot directly measure while the comet is hidden. Where are the jets located? How strong is the outgassing? Is it symmetric or wildly asymmetric? By the time 3I Atlas reappears in November, it might not be where our predictions say it should be. Astronomers will point their telescopes at the calculated coordinates and find nothing. Empty space. They'll have to search an expanding area of sky, hoping to reacquire the comet. Hours might pass, days even, and when someone finally spots it, they'll measure its new position and calculate how far it drifted. If the drift is only a few thousand kilometers, then that's manageable. Orbital elements get refined, tracking continues, no major drama. But if the drift is large? If 3I Atlas is tens of thousands of kilometers away from where it should be, that indicates something dramatic happened during perihelion, a major outburst, sustained asymmetric jetting, or something else entirely, and we'll never be able to fully reconstruct what happened. Non-gravitational forces get parameterized in orbital solutions, but those parameters are averaged over the entire observation period. For an interstellar object, this loss of trajectory continuity is especially devastating. Scientists want to trace 3I Atlas's path backward through the galaxy, to understand where it came from and how long it's been wandering. Precise trajectory determination requires observations spanning the entire passage through our solar system. Any gaps introduce uncertainties that propagate both backward and forward in time. If 3I Atlas's trajectory drifts significantly during solar conjunction, it could throw off calculations of its interstellar origin point by light years. Researchers might identify the wrong region of the galaxy as its birthplace. They might calculate the wrong ejection velocity from its parent star system. The entire story of where this visitor came from could be built on flawed assumptions because we missed 5 crucial weeks. And then there's the possibility that nobody wants to say out loud: what if 3I Atlas emerges from perihelion having changed velocity in ways that cannot be explained by normal cometary outgassing? Avi Loeb's paper asked whether 3I Atlas could be alien technology, noting its statistically improbable orbital alignment and its perfect timing for a hidden Oberth maneuver. If the post-perihelion trajectory shows evidence of deliberate course correction, the implications would be absolutely staggering. And we probably aren't ready for that. So here we are. 3I Atlas has been making its closest approach to the Sun, and we've been completely blind to what's happening. By October 29th, this interstellar visitor will reach perihelion at roughly 130 million miles from our star. These nightmare scenarios we've discussed in this video could already be happening to it. But we won't have answers until mid-November, when 3I Atlas finally emerges from solar conjunction and becomes visible in the pre-dawn sky. NASA's JUICE spacecraft will attempt the first post-perihelion observations on November 4th from 64 million kilometers away. Those images could reveal dramatic transformations, or something we never predicted. In December we'll know, or at least we'll know more. The story of 3I Atlas represents something profound about our limitations. We live in an era of unprecedented capability. Space telescopes, planetary probes, ground-based instruments of staggering power. Yet we can still be rendered helpless by something as simple as the sun's glare. But maybe that's fitting. Comets have always been objects of mystery, harbingers and wanderers appearing and vanishing according to their own schedule. 3I Atlas carries within it chemical fingerprints from planetary formation that occurred billions of years ago in a completely different stellar environment. Whatever transformations it undergoes during its hidden perihelion passage, it's all part of an ancient story that began long before our solar system existed. And perhaps the most unsettling thing about this entire story is the forced patience, the unavoidable wait, the knowledge gap that no technology can close. The universe keeps its secrets well, and who knows? We might just have one hiding behind the sun. Thanks for watching. See you in the next one.